All right, so let us finish now the module 1 and 2. So just give me a thumbs up again, just to let me know that you guys are already ready. Okay, so 7 out of 13. So the others are not yet around, I guess. Well, anyway, so we will continue with or without them. All right, so any questions so far when it comes to this example number 4? Okay, so none, I guess. So if you have a question, so feel free to ask me anytime, okay? All right, so moving on to the example number 5. So an electric motor drives a mechanical load taking 18.8 amp from a 230 volt source. So the question here is to calculate the power input to the motor. Second here is the horsepower output if it operates at an efficiency of 86.4%. Well, as we may already know, the formula for the power is P is equal to E times I. So just use this formula and then you will already get the power input on that specific motor. So P in or input is equal to 230, which is the 230 voltage source. And then 18.8 is the current, okay, the letter I, okay, of that specific mechanical load or that specific motor. So 230 times 18.8, just use your calculator and then you will get 4,320 watts. Okay. And then for the P out, so it says here that the horsepower output, if it operates at an efficiency of 86.4%. So this is the 100%, okay, 100% efficiency, 4,320, but we should only get the 86.4%. So that is why you have to multiply that one by 0.864 and then divide that one to 746, okay? Because the one that's being asked is the horsepower. And then again, 1 H, I mean, yeah, it's correct. 1 watt is equal to 1 over 7 or 746 horsepower, okay, or 746 watts rather. Okay, there's one right here. So 1 HP or 1 power is equal to 746 watts. So that's the reason why we have to divide that one to 746 because we wanted to get the horsepower value of that one. So just do the math again in here and then you will get 5 horsepower. All right. Okay, so are we clear so far regarding with the example number 5? All right, so in here, if it doesn't ask you to get the 86.4 efficiency, then just remove this one, okay? Just divide that one by 746, then you can already get the horsepower equivalent of that power, all right? So for the example number 6, what is the resistance of a load that takes 2,500 watts from a 115 volt source? So in here, you can use this formula. Where is it one? Here. So this one came from P is equal to E squared divided by R. So once you learn the logic behind that, then I guess you can uh, interchange those given variables. So in here, you can use R is equal to E squared. Oops. Is this the question? Yeah. R is equal to E squared divided by P. Is this the question? Yeah, number 6. And then E is 115 volts, so just square that one. And then divided by 1 by power, which is 2,500. And then just do the math using your calculator, and then you will get 5.29 ohms. Okay, so you can also identify the resistance if you have a given voltage and then a given power. Okay, not just using the Ohm's law, because if it's Ohm's law, then R is equal to voltage divided by current, wherein current is not available, so that's not an option in here. So the only one that is given is the power, and then the voltage source. So with that, you have to use this specific formula right here for you to be able to get the ohmic value of that resistance. Okay, so are we clear so far regarding with the example number 6? Okay, great. So I hope the others were also able to follow. Anyway, let's now talk about electric energy. So we're now done with the power. However, power is still connected with the electric energy. Okay, because there's still a voltage and then there's still a current. Okay, so in here, since power is a time rate of doing work, sometimes it's stated as a rate of expenditure of energy. Okay, so if there is a power, so there is an energy that's being used on that specific work. So it should be clear that electric energy is the product of power. Okay, so if you have a power, you're creating also an energy, wherein you can use that energy to, do something. So in our case, we need food, we need water. So those are our main source of, let's say, voltages, and then let's say the current is the flow of blood. So with that being said, we can now provide in an energy to our body. Okay, because if you're not going to eat, and then of course you will become thin, and then you will lose a lot of power in your body, and then you will die. Okay, so assuming constant electrical quantities during a period t or the second. Okay, so in here we have a watt, or 1 watt is equal to 1 power, just like what I mentioned a while ago. But since, for us to be able to get a specific value of energy, you have to multiply that one by time. Okay, so the longer the time, the more energy that's being provided. Okay, the larger the power, of course, the more energy that's being provided in there. Okay, so that is why in here, just by substituting the value of P, which is equal to EI, you can have this formula right here, EI times T. Or you can have this formula right here, I squared times R times T. Or you can also have this formula right here, E squared divided by R times T. So in other words, you just have to multiply uh, time in all of your formulas before. Okay, so initially we just started with 1 watt is equal to 1 power. Okay, wherein just multiply P, then you will get electric energy. Okay, so moving on, we now have here the kilowatt hour. So again, we have 1 watt is equal to 1 power. Okay, or this W is equal to power. Okay, and then of course you wanted to have a time wherein, let's say, the unit for time in here, it could be second, could be hour, but let's just use hour. Okay, since that's the one that's being used when it comes to calculating a kilowatt hour, when it comes to our electric bill. So the one that we're reading is kilowatt hour, not kilowatt per second or not kilowatt per minute. It's kilowatt hour. Okay. And then in here, since we're talking about kilo, so as you guys may already know, 1,000 is equal to 1 kilo. Okay. So this one is the same with 1,000 is equal to 1 kilo ohms. All right. And this one is 1,000 is equal to 1 kilowatt. So if you want to get the kilowatt hour, just divide this one by 1,000. So why divide? That's because we read this one kilowatt per hour. So that is the reason why it should be divided by 1,000. Okay, not multiply by 1,000 because this one is being read by kilowatt per hour. So just divide it one by 1,000, and then you are now getting the value of kilowatt hour, or kilowatt per hour. All right. So were you guys able to follow so far? And how did we come up with this kind of formula? Hello, hello. Well, anyway, so if you're confused, again, you don't need. If you don't need to learn the derivation and how did we come up with this kind of formula. As long as you know that kilowatt hour is equal to P times hour divided by 1000, then you're good to go. Okay, so yeah, that's already it. So let's have an example for this one. So how much electric energy in kilowatt hours is delivered to an electric motor during an 8-hour period when operating from a constant 230 volt source if the average currents are 34 amp for 2 hour, and then 38 amp for 1.5 hour, 26 amp for 4 hour, and then 12 amp for 1.5 hour. So if you're going to get this one half, 4 hour, 1.5, 2 hour, you will get exactly 8 hour in total. Okay, and then here are the averages that they have consumed. Okay, when it comes to power. So I mean when it comes to current rather. Okay, so 34 amp, which is running 230 volt, and then 38 amp, which is running at 230 volt also, and then 26 amp, which is running at 230 volt, and then 12 amp, which is running with 230 volt source. Okay, so with this one, just use this formula right here. So energy is equal to 230, so that's the power, okay, which is this 230 right here, multiplied by the current. Okay, ups, my bad. Okay, this is not actually the power, this is just the voltage. So with this one right here, so remember that P is equal to E times I. Okay, so we need the power, right? So we need to have the voltage and then the current, which is the E and then the I right here. Okay, so that is why we have 230 times 34, and then the hour that it has consumed, which is 2 hour. So the same with the others, 230 times 38 divide, I mean multiply to 1.5 because it's 1.5 hour, and then 230 times 26 times 4 hour, and then 230 times 12 times zero point 0.5 hour. Okay, and then since we're being asked to get the kilowatt, okay, kilowatt hours, so we have to divide this one by 1000. Since that's the given formula, just apply this one and then you will get 54.05 kilowatt hour. All right, so I hope you guys were able to get this one. Well, you can just go back with this example if it's not clear to you. So did you guys get this one so far? So I'll give you 1 minute maybe to analyze. All right, so there were at least three who were able to get this one, and then the others, so I'm not sure. Just ask a question in my canvas if this one is not clear to you, and then maybe I could help you so we can have a short Zoom meeting if you want. Anyways, that's it for the example number 7. So example number 8 is another activity that you need to answer on the canvas. So I will leave the reading part to you guys. Just analyze this one later on after our meeting. The next one and the last is actually the heat energy. So if we have voltage and current wherein it can provide power, and at the same time it can provide electric energy, it could also provide heat energy. Okay, so heat energy is a current through a resistor, always involves a conversion of electric energy into heat energy. Okay, so if the heat energy raises the temperature of transmission line conductors or windings of motors, electromagnetism, or other electric devices whose function is to do work not related to heating, it is proper to regard it as an energy loss. In other words, oops, where is my cursor? In other words, when we say heat, okay, heat energy, so you need a resistance for that, okay? So I'm not just sure if you guys have already held a resistor, like after it's being used, it's actually super hot, okay? And then the one that it's being limited. Let's see. Supposedly, I is equal to voltage, right? So as our current will go up, our voltage will go up also. But since we have a resistance wherein it's a limiter, wherein supposedly they are 1:1, but let's say we have a voltage of 220, okay, and then you should also have the same value, but since we have resistance, then it will be divided by this R right here. So you'll come up with a lower value, okay? So while this one is being used, okay, this one is actually generating a heat, okay? So that's the purpose of that resistance. So those voltage or current is being transformed, okay, or being converted into heat. So since of course it's being converted into heat and that it's not being used in our electric circuit, so we consider this heat right here as a power loss, okay, because instead of having a 1:1 value, but if you want to have a 220 volts, sometimes you need a higher current or a higher voltage, like for example maybe you need 1000, okay, just to get the value of 200 because it will be divided into R. Okay, so I hope you guys are getting the idea. So in here, with that being said, so let's go back in here. So function is to do work not related to heating. So it is proper to regard it as an energy loss. However, where is that one? However, on the other hand, if the heat energy is made useful, like for example, it's a water heater, a toaster, a percolators, flat irons, electric furnaces, uh, anything that provides heat that is being useful, then that is not considered as a heat loss anymore. Okay, because they are being used. That's their purpose. Okay, so the latter is generally referred to as a power loss if during the period of operation the power is constant. So in here, it's just being considered as a power loss. Like for example, the time that you're not using that heat power anymore. Like for example, using the flat iron. So not all the time you're using that flat irons. There are times that you're not constant, you're not consistent. So you will put it on one side and then it's still running. Then that's again a power loss. But if you're using that heat, then that's not considered as a power loss. Okay. Well, anyway, that's it for the heat energy. And then here's the computation on how to get the heat energy. So this one came from the power, which is I squared times R. P is equal to I squared times R. All right. But when it comes to solving a power loss, so we are actually getting a wattage. Okay, so depending on the value of your R, so the higher the value of your ohmic value, okay, the higher the wattage loss. Okay, that's the one that we're saying power loss. Okay, so that's in a transmission line having a resistance of 0.03 ohm. So this is already small value when it comes to resistance and carrying a 150 amps. So the power loss will be, just use this formula. So I squared times R or 150 squared times 0.03. So the power loss is 675 watts. Only if that heat is not being useful. But if it's useful, then this 675 is not a power loss. Okay. So I hope you guys are getting the idea. And then at the same time, of course, the higher the resistance, the higher the power loss. Just imagine if this is 3. So 3 times 150 squared. So 3 amps. I mean 3 ohms. 3 times 150 squared. So there's a power loss of 22,500 watts. Okay, so that's the power loss that you will get if you're not using that power hit that's being provided by that specific, uh, let's say, device. Anyway, so here's another formula when it comes to getting how many gram calories that you need before you can raise a temperature of, let's say, in Celsius or in Fahrenheit. So in here, when electric energy is applied to useful heating, such as water heater, it is desirable to know how many gram calories or British thermal units, or BTU, okay, of heat energy are represented by 1 unit of electrical energy. So precisely performed experiments have shown that 1 watt sec of electric energy, or 1 joule, is equivalent to 0.24 gram calories. So again, you don't need to know how did we come up with the 0.24. So they're the one who started with this one. Well, if you want to know the derivation on how did they experimented, how did they precisely perform just to get this value of 0.24 gram per calories, then feel free to do so. However, all you need to do is just to memorize the 0.24. This is just a multiplier. Okay, so 0.24 is equal to 1 calorie. Okay, so applying this conversion unit to our equation, you will get this one. So before, we only have power times time. So in order for you to get the heat, so you have to multiply that one on or to 0.24. So heat is equal to 0.24 power times time, or heat is equal to 0.24 voltage times current times time, or 0.24 times I squared times resistance times time, or 0.24 times E squared divided by R times time, and then calories. Okay, so the unit for the heat is calories after it's being multiplied to these given formulas. So just take note that 1 gram calorie is, you will get, say, Celsius. Okay, 1 gram of water is 1 degree Celsius. So in here, if you want to get the specific amount of heat energy or gram calories that you need, just multiply that one by 0.24. Okay, so BTU is just a term for Fahrenheit. They are just the same, you know. It's just that when we say BTU, we're talking about pounds, not grams. Okay, but basically the concept is the same. So 1 pound of water is 1 degree Fahrenheit. So either of those two, if you need a value of, I mean, a unit of Celsius, then you can use gram. But if you need the unit of Fahrenheit, then you need pounds for that. So just convert this one to pounds or convert this one to grams, depending on the question, okay, on what is being asked. Well, anyway, so yeah, that's it for the heat energy. So I didn't include a example here anymore, since all you need to do after getting the power, or to be short, this one is electric energy. Okay, P times time. Just multiply that one by 0.24, and then you can now get the heat energy. All right, and then that's it for this module 1 and 2. Okay, so before you guys go, may I remind you guys that you have 4 given activities. So exercise 1 and 2, example number 8, and then the quiz for this one, which is just a series and parallel circuit connection. And then the case study number 1. All right. So yeah, that's it for the week 1. So next meeting, we'll now discuss the week number 2. So we'll talk about Kirchhoff's law and then the Maxwell loop current method. So any questions so far regarding with our discussion or regarding with our module? Question or clarification? Anyone? Hello? You guys still around? Okay, so an answer coming from Mr. Aaron. Alright, so if you guys don't have a question anymore, then we'll just meet later on the laboratory. If ever that you have a laboratory subject. So that would be on 3:30 p.m. Okay, so goodbye and thank you guys for coming. I really appreciate it. Goodbye. Goodbye and thank you too.